So the basic idea is to utilize methods from quantum gravity to investigate gravitational subsystems on the null cone, on the light cone. And this is useful because on a light cone there's basically more structure for us available, structure that we can use in classical general relativity to understand physical observables such as radiation and power, so emitted power, the power that gravitational waves can carry. And what I can tell you about is a potential non-perturbative quantum gravity effect in which there is a bound on the luminosity, so the radiated power of gravitational waves, which is really based on completely non-perturbative results. And these developments build upon a lot of earlier work in the literature, both in loop quantum gravity in the context of isolated horizons, but also within the wider community, including this community, of course. So about quantum, especially there is a connection also to quantum reference frames, which we will see. So what luminosity? So what is luminosity? Luminosity is energy per, is power, so energy per time. We believe in quantum gravity that the relevant scale for quantum gravity effects is the Planck scale. From h bar, Newton's constant g, and the speed of light c, so Planck constant, Newton's constant, speed of light, we can build new physical units, the Planck units. And now something funny happens in 4 space-time dimensions, and it is in 4 space-time dimensions only. So if you take the, so if you want to speak about power, we should speak about energy per time. So take Planck energy per Planck time. So what do you get? You get Planck power. The Planck units exist in any space-time dimensions, also in higher dimensions. But what happens in d equal 4 space-time dimensions alone, so 4 space-time dimensions are strangely special in that sense, is that the power is actually, the Planck power is actually independent of h bar. So it can already appear at the classical level. If we consider, in fact, 2 coalescing black holes that can radiate gravitational radiation, the emitted power will go through some profile, and at some point there will be a peak luminosity, so a maximum brightest power emitted. And this peak luminosity, whatever it is as a function of physical observables, we can always write in terms of this Planck luminosity times some scale-independent functions. And since now there's already at the classical level a natural, this constant available, this equation makes actually totally sense at the classical level. And it has people suggested, or people found it suggestive from that, to conclude that there is in fact an upper bound for the emitted power, that the Planck power bounds the luminosity of gravitational waves. And what is exciting is that, gravitational wave events are the most powerful, most luminous events that we see in nature. And we came actually very close to this. So the question now for us is, as researchers in quantum gravity, I believe, is there actually, could there be a quantum story behind this luminosity bound? This seems a bit strange at first because, well, there is no h bar. But so people first tried to understand this bound purely classical. And there's a simple argument, in fact, if you look in the big book of Misner, Thorn, Wheeler, it's somewhere hidden, just a little paragraph. But I won't go through this argument. It's really not very difficult. You take the quadrupole formula for gravitational wave emission that Einstein knew. So the third time derivative of the quadrupole moment of your radiating source squared gives the emitted power. And then you take also into account that the system is bound by gravitational forces. And then you can eliminate one of the constants that appear, one of the parameters that appear here. And then you say, well, so the emitted power will increase as the system gets, as the two masses get closer and closer, but no power can be emitted once you form a black hole. In other words, once your mass is confined to a region smaller than the Schwarzschild radius. And this gives an inequality, and if you plug everything together, you get a bound. But now there's actually a problem, because if we look at the gravitational classical phase space, then it turns out that there is not really a good reason for such a bound. So there are counter arguments in classical general relativity why this bound is not there. So there are some papers on that. Furthermore, if this is a quantum gravity effect, it's somehow strange, because there's no, in this equation, there's no h bar. And furthermore, it cannot, so if it is a quantum gravity effect, it can only be a non-perturbative quantum effect, because perturbative quantum effects of gravity are those where we look at the h bar expansion. So this can only be a non-perturbative effect. So how could this possibly arise? And the argument is the following. So normally, when we think about a radiating system, we try to model it, no, by two masses that spiral together. But there is a very powerful formalism in mathematical relativity, the Bondi formalism, that allows you to go far away from the gravitational sources. So you don't really need to understand what happens here inside, where these masses coalesce and emit gravitational waves. It's actually, you can kind of switch around the perspective and study the system from infinity and then move inwards. And then the way to describe gravitational wave luminosity is in terms of the geometry of null surfaces, null congruences, in fact. So how two neighboring light rays behave geometrically. And there's one quantity which is called the shear, and the shear tells you how, what gravitational waves do, no? So if you have like a round assembly of test masses, this gets kind of squeezed and bumped. And this is described by the shear. And then it turns out that the shear squared is the gravitational wave power, asymptotically. So all these quantities have a specific fall off, so a specific expansion in 1 upon r, where r is the distance from the source, basically. And so now let's say we are not at asymptotic infinity, but at the finite boundary. And then if you take these fall-off conditions, you can actually write the emitted power as some quotient, the quotient of the shear divided by the expansion. The expansion tells you how the two-dimensional area of these cuts of the light cone changes in time. And now, so now you have this fraction, this ratio between shear squared and the expansion squared, and it gives you asymptotically the emitted power. But in the S-matrix approach of perturbative gravity, the denominator is to leading order in the expansion, just a constant, a C number, a classical number, nothing quantum itself. But in a quasi-local approach, where in a sense we take the gravitational subsystem to be primary, so we kind of switch perspective. We are not asking how to define a gravitational subsystem. Rather, we say the gravitational subsystems are just the fundamental building blocks of quantum gravity. And then at that level, which is kind of what loop quantum gravity does. So spin network states have finite, don't represent asymptotic asymptotically flat quantum geometries, but something more non-perturbative. And so therefore one should expect that this is a quantum thing, and also upstairs there's a quantum thing. So this limit at the non-perturbative level has takes different variables as quantum, while at the in the perturbative regime we assume them to be classical, and this could lead to a contradiction. And this is basically the mechanism that I see. So now let's get a bit more into the mathematical details. So what we want to understand are gravitational subsystems. But now I say, let's not do this on a spatial hypersurface. Let's do this on not the three-dimensional spatial hypersurface in spacetime. Let's put this at upside towards the light cone. So let's understand the gravitational subsystems on null geometries. And topologically, and this is in fact all the structure that helps us simplify the analysis. On a space-like hypersurface, you're basically just floating around in the universe, but here there's more structure for us available. What is this structure? Well, these are, so topologically, you can think of a light cone as a cylinder, no? So a two-dimensional sphere, and then you illuminate this sphere and light rays go out. And these light rays I picture here as these vertical lines. So mathematically, this is what is fiber bundle. And now we want to describe the geometry. The geometry of, in gravity, gravity is encoded into geometry. We want to do gravity on a null hypersurface, so we encoded gravity into the null surface geometry. And but now light rays, have zero length, so we have to deal with a metric that has one degenerate direction, one zero direction, which is of course the direction of these null generators. And just like in 4 space-time dimensions, we have tetrads, orthonormal frames. On the light cone, we also have orthonormal frames. A dyad, so a dyadic basis, 1 and 2, let's say, on any two-dimensional cross-section of this null cone. And this dyadic basis can be parameterized by an overall conformal factor. This determines the kind of size of small triangles of this cross-section, and a matrix as in SL2R. And this matrix, these SL2R variables, they describe like shear degrees of freedom. So how the shape of this two-dimensional, the shape degrees of freedom that characterize the metric at the boundary. But now the Einstein equations actually put constraints on these variables. So what we have is, and on top of this, we actually need a notion of time along this, along each null direction. So there's no natural notion of time along a null ray, so we can choose any one that we wish. The one that actually simplifies our analysis is one which are not what we call in relativity affinely parametrized, but these are null generators that are that have a non-trivial non-affinity given by the expansion, basically. And then this defines a clock for this subsystem, and the rate. Then we introduce an auxiliary unphysical time coordinate, and the rate at which this clock ticks defines a new field for us, which I call the chronoton, so time thing, basically. And then all these variables need to satisfy certain constraints. This is now an important point. The other one is just kind of kinematical. And this equation is one of the Einstein equations, one component of the Einstein equations, and it's in fact the only constraint that you need to impose on these kinds of variables. This is the so-called Raychaudhuri equation, and it tells you how the area of this two-dimensional geometry. So imagine you have a light cone, and you have two-dimensional cuts, and this equation tells you how the area of these two-dimensional cuts that may have the topology of a sphere change in time. So the second, what does this equation tell you? It tells you that the second time derivative of this conformal factor omega is given by the shear encoding the action of gravitational waves passing through the null cone. So if a gravitational wave passes through this cone, these little triangles, the two-dimensional geometry is kind of squeezed. And this squeezing is encoded into these shear variables. And conjugate to this shear is so now we have a phase space. So we have this group value data, and conjugate to it is, so we have now like an SL2R phase space, and conjugate to this SL2R group element is an so in the phase space sense, is an SL2R Lie algebra valued element, Lie algebra element. And that one we can always, this is a bit like the Schwinger representation of SU2. This you can always parameterize in terms of some sort of Schwinger valued Schwinger fields, like in terms of spinos. This is just like saying an SU2 Lie algebra element you can always write as the square of some two spinos, no? Something like this. And similarly, if now the Lie algebra element is not in the SU2 Lie algebra, but in SL2R, which is the same as SU11, you can do the same. And what is now interesting is that these fields, starting from the gravitational phase space, satisfy very simple Poisson bracket commutation relations. And starting from the gamma Palatini action that we use in loop quantum gravity, these turn basically into sort of oscillators on the light cone. And so what happens now is quite intriguing. So we have an area operator for these two-dimensional cuts, which is basically just, which is really nothing but a number operator. This is phase space geometry. You don't need to understand all these details. So what it really means is that the area is AA dagger, a number operator. Similarly, the expansion, so what do I mean by expansion? The expansion says you how the area of so these are, in space-time, are spheres. And the area of these spheres can grow or shrink, so there's an expansion. And once again, this turns into a sort of number operator, where gamma is a parameter that appears in loop quantum gravity, the Barberon immersive parameter. And in addition to that, there are these shape degrees of freedom, which are now encoded into these spino-type variables, like in oscillators. And on this phase space, we have to impose constraints. This is just to tell you where this parameter comes from. I won't go into the details. But now we have a Hamiltonian constraint in terms of these oscillator type of fields. Okay? So this is now important. So we have just like on a space-like hypersurface, we have a kinematical phase space and constraints. Now also on the null hypersurface, we have a kinematical phase space, but the true physical phase space is only a subset that we find by imposing a constraint. What is this constraint? This constraint generates diffeomorphisms, but only along the null generators. So reparametrizations in time, but in this null time. And now, actually, what happens is that you can realize that this is really, so the Poisson brackets that these generators satisfy using a mode expansion are in fact just so-called Virasoro generators. So you basically get a conformal field theory along each null ray. Not for an isolated horizon or a black hole horizon or specific asymptotic boundary conditions, but for any null hypersurface. And now the idea is, well, we can just look into mathematical physicists' textbooks to learn about a bit of quantum field theory, and then try to find representations of these generators. But now there's a problem. So we have introduced these new fields. We know that gravitons are bosons, but these fields are kind of, gravitons are only composite of these. So at this point, we don't know what is the fundamental statistics for this. But there is a hint, so we can try to, there is in fact, so one of the observables that we have in this CFT is just an abelian current, sort of number operator. And this abelian current is related to the SU11 Casimir. And the SU1 so pi is the momentum conjugate to this SL2R that I have on the null cone. This SL2R encodes the shape degrees of freedom of the geometry. So the geometry modulo a conformal factor. And what I now get is a bit crazy or scary, maybe. So there's this momentum variable, and out of this momentum variable, you can generate a Casimir, SL2R Casimir. Now, L and C, these are just algebraic quantities. They satisfy certain commutation relations. But in terms of the geometry, so the geometry is written down here. So in terms of the conformal factor, in terms of expansion and shear, so the geometry of the null hypersurface, you can write this Casimir in terms of these variables. Notice that here, suddenly the Barbero immersive parameter of LQG appears. And what I now find is that if I choose bosonic commutation relations, the CFT has actually somewhat of a problem because the central charge is negative, and then the mathematicians tell you, or the theoretical physicists, that, well, the underlying CFT is non-unitary. So this is not really quite working, the negative norm states. But this can be avoided if we choose Fermi statistics for those fields. And if we choose Fermi statistics, then what happens is that this Casimir suddenly can only fall in one case, in one category, namely when L squared is always larger or equal to C bar. And this turns into an inequality for expansion and shear, okay? And if we now, what does it mean? Well, this means that on any null hypersurface, we have to, at the quantum level, we need to satisfy a certain constraint, a certain inequality, that the shear is always bounded by this inequality. But now this should happen now this should happen for any null hypersurface, especially also those that we send all the way to null infinity. And if we do this, we get a constraint or a bound now, really, on the radiated power. So we get that the emitted power of these gravitational waves should be bounded by this Planck power, and then there's also this funny dependence on the Barbero immersive parameter. Conclusion. So what I've later sketched, sort of, is a non-perturbative quantization of null initial data, utilizing methods from different approaches, actually. And the spectra, but however, confirming earlier results. For instance, what I find is that the spectra of geometric observables, like the area, is in fact compatible with the LQG discreteness of geometry. But on top of that, I also find a quantization of shear, so of the radiative degrees of freedom of general relativity. And thereby, so now I had some arguments for such a luminosity bound earlier, but it was developed in a much bit more hand-wavy way, now using more like CFT methods. But what I've, okay, so you can say maybe all of this is not really trustworthy, but what it shows is an implicit proof, so it's a counterexample, an implicit proof that something that we need to be perhaps a little more careful, that when we do like perturbative gravity, quantum gravity, when we do the S-matrix approach, that in fact there are two limits involved that may not commute, namely the asymptotic R going to infinite limit and the semi-classical H bar to 0 limit. The logic is, of course, fundamentally is quantum theory, but the logic that I came from is the following. So I look at the subregion phase space, the phase space of general relativity in a finite domain, but not a spatial domain, but a null domain. And then I quantize this phase space, and I get some quasi-local quantization. No? And in this quantization, there is some bound on the luminosity. But one could have done, which then would go on all the way to, would also affect the theory at large distance. On the other hand, what one normally does, I mean normally like high energy physicists and in the perturbative approach is a different viewpoint. There the starting point is actually the physics at infinity. So one first goes at the classical level to an asymptotic boundary and then quantizes this asymptotic boundary, obtaining graviton S-matrix elements. And what I think perhaps the main lesson of this presentation, of this analysis, is that these two limits may actually be in conflict. And I think this is a very interesting lesson for us. Thank you.